All right, I want to just kind of summarize a couple of cool takeaways for us at the end of this section. So we're going to write down a couple facts over here. So we've seen some particular examples of looking at examples with finding winners under various methods and then asking, does this method in this example satisfy or violate the majority criterion and the head-to-head criterion? One of the things that a mathematician would then do is start to look at that method very holistically, to think about, is it even possible for it to violate it, or is it forced into satisfying the method? So does it have the potential of violating that criterion or not? So we're going to write down some of those results. So let's go across the majority criterion first. And I have our 4 voting methods here. So we're going to ask the question of, does it always satisfy the criterion, meaning every single example we can come up with, it's always going to satisfy the criteria? Or is it possible to come up with examples where that method violates that criteria? So let's think about majority criterion. Well, majority criterion, right, says if there's a candidate who has majority, they should be declared the winner. Now, if we think about plurality method awards the winner to the candidate who has the most first choice votes. Now, if someone has majority of first choice votes, you can think about it, they already have over half. It would be impossible for anyone else to have more. So majority is going to be the most. It will be plurality. So it's not possible for this one to award anyone else to be the winner, which is kind of cool. So we would say that this is a situation where this always satisfies the majority criterion. It's impossible for it to violate it. Plurality with runoff, well, if you remember how that one worked, right? It had a catch at the very beginning of it. It said if a candidate has a majority of first choice votes, declare them the winner. We're done. We don't even do the runoff election. So clearly then, if a candidate does exist that has majority, they're going to be declared the winner in this plurality with runoff. So this one also always satisfies the majority criterion. Now, border count's a little harder to think about holistically, except remember, we saw an example. We did an example, the one with the omelets, where we did border count, and the omelet that had majority, the candidate that had majority, did not win. So right there, automatically, it means it's possible to violate this because we saw an example. What these ones are saying is there are no examples, they just don't exist. So this one, border count, can violate. Now that doesn't mean that it always violates. We also saw examples where it didn't violate, but it's possible to. Now the last method we learned was pairwise comparison. This one also can be a little bit harder to think about, but kind of the way to be convinced of it is if a candidate does have a majority of first choice votes, it would be very hard then, right, if you then compare that with one other person. Well, this person already has a majority of first choice votes, so they're going to have a majority of the votes in every single head-to-head that they're in. So they're going to win every head-to-head that they're in, which means that they're going to win the most points overall, and they would be declared the winner by pairwise comparison. So this one also always satisfies the majority criterion. Now, there are other voting methods we can learn that we could look at the majority criterion with, but instead what I want to do for a minute is switch over to thinking about the head-to-head criterion. So this one asked about, is there a candidate who wins head-to-head versus every other candidate? So they win all of their head-to-head comparisons. Would this method declare them the winner, yes or no? So it turns out this one is actually really hard to satisfy. So this head-to-head criterion. It turns out that plurality can violate it, So it's possible to have someone who does win head-to-head against everyone, but yet they don't have a plurality of first choice votes. It's also possible for plurality with runoff. This one can violate. So it's possible to come up with examples where there is that person who wins head-to-head against everyone, but then they lose in plurality with runoff. Board account also can violate. So when we count up the points, it's possible that that person is not declared the winner. But when we get to pairwise comparison, well, these two things are very related to one another. So the head-to-head criterion says the person who wins the most, or not the most, but if they win all of their head-to-heads, then they should win. And pairwise comparison awards the person who wins the most head-to-heads as the winner. And so if you win all of them, everyone else lost at least one, so you'll have won the most. So this one does always satisfy. Now, what we're interested in then is this idea of kind of analyzing fairness of different voting methods. So we start to get these ideas of how do we determine what methods are best, if you will, are the most fair. They're going to give the best indication of the people's will by awarding a winner. And so what we see is this idea of, well, violating fairness criteria is sort of like a negative mark against that method. But yet there are other things we look at too. So there are many more fairness criteria besides what we've looked at as well. So far we start to see like, well, pairwise comparison has some pretty good standing so far. Board account has a couple issues, but yet we also kind of like board account. It kind of works pretty well. And so we get these interesting feelings here. So there's a really interesting theorem that I just want to explain to you quickly, kind of what it says. It's called Arrow's impossibility theorem. So this was developed by a man named, his last name was Arrow. And what this theorem talks about is it says that there is no possible voting system that always satisfies every fairness criteria. That's why it's called an impossibility theorem. He's saying it's impossible to come up with a voting system that satisfies every fairness criteria. In particular, he looked at 5 different criteria, but then we could expand that. Then that if we can't satisfy those 5, then we can't satisfy all of them. So something even like pairwise comparison, right? So far it satisfied these 2 that we look at, but there will be a fairness criteria that it can violate. An interesting one with pairwise comparison, just to explain to you, is called the independence of irrelevant alternatives criteria, which is a long and fancy name, but one of the parts of that criteria has to do with, well, if I have, say, like some candidate in the race who never was going to be a winner and I take them out of the race, just remove them from the election, it shouldn't impact who won, which kind of makes sense. But yet, this pairwise comparison method has the possibility that taking someone out of the race could then take someone who was a winner and switch them to a loser. By all you did was take someone out of the race, which is kind of interesting. That one actually is a really hard fairness criteria to satisfy. There's very few methods that satisfy it. So one of these ideas that kind of a different way to describe Arrow's theorem is kind of in essence, there is no perfect ranked voting system. So when we are talking about Arrow's theorem, we are also always talking about these types of voting systems that we've been learning about, where we're ranking candidates, we're filling out some sort of preference ballot. So this would not apply to different types of elections, like there's situations where you might do like a score voting, like if you watch diving in the Olympics and someone does a dive and then they hold up, the judges hold up a number to give them a score, and then the person with the best score wins. That doesn't fit in this realm of ranked voting system. So Arrow's theorem wouldn't apply to that type of a system. But all of these, what it's saying is not just the ones we've learned so far. There isn't one that satisfies it. What he proved is that it's not possible to create a system that's perfect. So no matter what, we're always going to have flaws in our system, which is a really interesting thing to think about. So it really gives us this idea that no matter what, we really have to think about our particular scenario that we're in, and we're never going to have a perfect system for it, but kind of what's going to get at the heart of what we want for that example, for that scenario. So what will be sort of the best in the situation? Now, another important fairness thing that we haven't necessarily talked about yet is we've seen lots of examples where if we run a different method with the exact same set of ballots, we get a different winner, right? That happened in lots of our examples, which means it's really important to know the method before the election starts, because otherwise people could be very unethical. And if you pick the method after you have the ballots, you might be able to manipulate having the candidate that you want to win by choosing a method based on the ballot. So you would really need to make sure that you know it beforehand. So there's a ton of really interesting fairness and ethical questions that come in when we talk about voting, about how to make these voting methods really more indicative of what the people's wishes are, and then really try and make them to be, like I said, the best for the scenario that we're looking at. A really cool topic. If you want to learn more, there's definitely lots to look into. There's even more in the book that we didn't go into, but a really, really cool topic to think about.